Okay, welcome to the e-learning of PC 3110. We are doing gravitation discussion questions, and you should have tried these questions. If you are stuck and you need hints, please view as far as the hints, pause the video and try on your own. So here's the first question. So there's a satellite, okay, that is traveling in a circular orbit and is traveling at constant speed. And this is because A, B, C. Okay, and the correct answer should be C. Okay, there is no component of force along the direction of motion. So if there were a component of force along the direction of the motion, there will be work done. Okay, and because there's work done, energies added, the KE will actually increase. So by modus tollens, i.e. if X implies Y and Y false would mean X is false, there is actually no component of force along the direction of motion. So how do we think here? The trick in thinking is sometimes we need to consider the implications of the reverse of the statement that we are considering. Moving on, why does the moon not fall? Okay, the moon is always pulled towards the earth because there's a gravitational force between the earth and the moon. It does not fall towards the earth because, okay, A, B, C, D, and the answer is D. A is clearly wrong because the net force is not zero, as we have just mentioned. B, the pull of Earth's gravity is balanced by the centrifugal force. In the first place, we have not really covered centrifugal force in this module, and also, even if it's balanced, so what? Okay, C, the moon pulls back on the Earth with an equal but opposite force. Yes, it does, but so what? So let's see why, okay, the moon is constantly falling. So here, okay, we have a cannon mounted on top of a very high mountain. So if, okay, nothing happens and we just let the cannonball drop, it will drop right onto the earth. And we know that this is considered falling. If we give it some, okay, speed, okay, it will go in a parabolic motion as indicated by the yellow line. So we agree that this is falling. And as the speed tries to increase, it will actually trace, okay, this path is trying to fall towards the earth, but before it can reach the earth, it has already gone past the other side and it comes back. So what you have is an elliptical orbit. So do we agree that this is also falling? And if we give it even greater speed, it will start, this ellipse will be symmetrical, so it becomes a circle and it ends up here and it comes back. So this is also falling. And if we give it even more speed, it will go this way, then this way, then this way. So in all of these cases, okay, the moon is falling. So now we have the next problem, weather satellite. So we want to place a satellite into a circular orbit, okay, this height above the Earth's surface. What are these parameters? These are all the kinematics parameters and given this set of data. So let's take stock. What do we know? We know that the radius of the orbit is this. What else is given? We know that the mass of the Earth is given, and of course the gravitation constant is given. What should this solution involve? Since this is a circular orbit, clearly we need to talk about circular motion. And anytime we talk about circular motion, please remember what causes something to go in a circle is the centripetal force. So in our analysis, okay, it's likely that we are going to analyze the centripetal force given by this expression here. So we put the ideas together. What caused the centripetal force is actually the gravitational force. So, okay, we have this expression, and if we cancel m over r and if we take square root, okay, we'll easily get the answer. So to get the period, we can just simply consider the distance over time. Okay, the distance being the circumference of the circle, 2 pi r. Okay, sorry, the time is distance over speed. Okay, pardon me. Okay, 2 pi r over v. Okay, and this is the answer. So the acceleration will be this answer. So let's look at this planet's problem. Okay, so a planet is discovered, okay, going around this star. Okay, orbital distance is given, orbital period is given, asking you to calculate the mass. So when we study this topic, we need, in fact, any topic in physics, we need to know the relationships very well. So when you know the relationship, you know that the relationship between the period and the orbital distance is given by Kepler's third law. T squared is proportional to R cubed. So when you derive Kepler's third law, it involves the central mass. So the full expression is actually T squared equals to 4 pi squared over Gm R cubed. So once we know T, we know R, we know G, of course we know pi, and of course we know what 4 is, okay, we can find M. So once you see how this is done, this is actually very easy. Next question on lunar colonies. So, okay, once again, okay, here we have a orbital period given, which is T. Question asks to calculate the height, which is R, which is related to R. Okay, so we have this. Okay, we have this T and R problem. Hence, we get this. Okay, when we plug in all these values, we can easily solve for R. Actually, this is actually H. Okay, the R you get is a little bit different from the H here. And why is that so? Because you will need to subtract away, okay, the radius of the moon. So if we consider the order of magnitude of this value versus this value, okay, what do we have? This is the moon, and here's the orbit. It's going to look something like this. Okay, so now, next question. We have always seen astronauts floating around as if they were weightless. But are astronauts really weightless? The answer is they are actually not. So what happens is, okay, we are able to use proportionality to calculate the G, okay, at a certain height, and it is this. Of course, if you so choose to use G equals to Gm over R squared to obtain this value, please go ahead. Okay, so okay, there is some pull, and this pull is not insignificant compared to this value. So if we were to draw a diagram, okay, so this is the Earth, okay, and this is drawn to scale. Okay, 2,000 kilometers is about here. So 400 kilometers is about 1/5 of the way here, so it's somewhere around here. Okay, so it's so close to the Earth that there's no way, okay, there's no weight. So why do they appear weightless? Okay, it's not because there's no gravitational pull. It's because all of this pull, okay, is used to accelerate the astronaut. So there's also misconception that says that, oh, there's no gravity because there's no atmosphere. Please, okay, the atmosphere is not responsible for gravity. So, okay, remember I said that, okay, they are always accelerating, and this pull caused the acceleration. Now we compare this question to conceptual analysis 6.7, where we conclude that, okay, anything that's in orbit is always in free fall. So we are able to, okay, consider an analogous situation, okay, where the whole spaceship, okay, is falling together with the astronaut. So the analogous situation would be, okay, the lift cable snap, and whoever is inside the lift, okay, appears weightless for a moment because all of the weight is used to create the acceleration downwards. So in both cases, they appear weightless. That's the end. Thank you.